All right, we're going to get started. Thank you everybody to come to the short paper session on scientific and immersive visualization. I'm the session chair, Bei Wang. We're going to start with the first speaker, Michael, who's going to talk about accelerating transfer function updates for distance map-based volume rendering. Please go ahead, Michael.
Okay, thank you for the introduction. My name is Michael Rauter, and this work I'm very happy to present our work here. And this work was a collaborative effort between Lukas Zimmermann, Markus Zeilinger, and me. Lukas Zimmermann is affiliated with the Medical University of Vienna in Austria, and Markus Zeilinger and me, we are affiliated with the University of Applied Sciences in Wiener Neustadt, Austria. So the motivation for our work, we have the use case of interest of direct volume rendering in virtual reality, where we have two main priorities. Priority one is that we want to have the lowest possible frame rendering times, and priority two is that we want to be able to update the transfer function live with minimal impact to performance. We use empty space skipping to accelerate volume rendering, and the idea here is to skip sections along the ray that do not affect the rendering result during ray casting. And ESS based on the distance map outperforms other ESS types like block-based or octree-based ESS, which can be seen from benchmarks from literature. But the drawback, though, is that changing the transfer function requires to recompute the distance map. Our contribution is that we show how to accelerate the distance map update for distance map-based ESS, and therefore we are extending original work by Deakin and Naxted. And what you can see here is an animation playing the results of a renderer when the transfer function changes over time. The original method by Deakin and Naxted computes an occupancy map at reduced resolution. They use non-overlapping blocks of B cubed voxels, and they choose a block size for B of 4. The occupancy map specifies which blocks affect the rendering, and a block is considered occupied if any voxel inside the block gets mapped to a non-zero alpha value according to the transfer function. Otherwise, it's considered unoccupied and can be skipped when rendering. The process of creating the occupancy map is shown in the figure on the right on this slide. And eventually, they compute the Chebyshev distance map D derived from the occupancy map. And this allows them to skip several blocks at once when rendering. Our extension to this original method is that we divide the intensity space into partitions. The most obvious choice here would be to use a uniform partitioning as shown in the figure, but it might be beneficial to deviate a bit from this configuration. We have a one-time initialization step where we compute a separate occupancy and a separate distance map for each intensity subrange. We call these maps the partitioned occupancy maps and the partitioned distance maps, the POMs and PDMs. The only thing that we need to do when we want to do a transfer function update is that we need to combine those PDMs covering intensity partitions which can affect the rendering result according to the transfer function. This yields D prime. D prime is just the voxel-wise minimum over the PDMs with the index P of the set S, where S is the set of partitions that contain intensity values that get mapped to non-zero alpha values. D prime is in general just an approximation of the original distance map D. D prime is at every position smaller or equal to the original distance map. So it's impossible to skip too much space, which is good because otherwise we would introduce rendering artifacts. The higher the number of partitions is, the better D prime approximates D. A limitation of a method, though, is that only either all or none of the intensity values inside a partition can be skipped. That can lead to a performance degradation. We would like to refer to our paper for details and implications on this issue. If the intensity value ρmin encodes the empty space, it can be beneficial to reserve a unique partition for ρmin and to partition the remaining intensity space uniformly. This can increase performance drastically, as we will see in the results section now. The frame rendering time and the ESS acceleration structure update time is shown in comparison for different methods here. and the data set used was the stack beetle data set with the volume dimensions and the rendering resolution stated here. The GPU used to obtain the frame rendering timings was an NVIDIA RTX 4090 GPU. The transfer function used is also depicted here. And on the right side, you can see the figure, the graph of the frame rendering timings that we obtained for different methods. In red, the frame rendering timings for the comparison methods are presented, where we have no ESS, block ESS, and distance ESS. And the distance ESS is the original method of Deakin and Maxted. And our method, the timings for our methods are the blue and the green bars here. The blue bars being a uniform partitioning configuration for different number of partitions, and the green bar basically having this special partition for row min. And here you can also see this case where we have a performance degradation for the uniform partitioning case, but if we introduce the special partition for row min, then we get comparable frame rendering times to the original method. The yellowish bar here are the timings for the ESS acceleration structure update, and we can see that this is in the original method really a bottleneck. In our method, though, we managed to get much faster distance maps updates, and therefore we have improved the performance here. In conclusion, PDM ESS allows for a transfer function update up to 30 times faster than before. Although D prime just approximates the frame rates are comparable if the number of partitions is reasonably high, and if we use a unique partition for row min in case that row min encodes the empty space in the dataset. Our method comes at the cost of higher memory consumption, although I want to point out that we only need to store the PDMs. The individual POMs can be discarded as soon as the corresponding PDM was computed. The extra memory demand of our method is num partitions times total number of blocks in bytes, and we use 8-bit unsigned integer distance map values with clamped distances. Yeah, the reference used in my presentations are presented here, and I would like to point out that our code is since today on GitHub, so please check it out if you're interested. Thank you for your attention, and I'm looking forward to your questions.
Thank you very much. Let me start with the first question. In one of your limitation discussion, you mentioned that only or none of the intensity bands could be skipped. Do you have any idea or strategy of what could be used to mitigate such limitation? Or if you are not planning to mitigate such limitation, is this a big sort of limitation for your approach?
Yeah, so a very good question. Actually, it really depends on the number of partitions. So if you decide to choose enough partitions and your transfer function is well behaving, not having too much jumps, it's really not an issue at all, as can be seen also in the from the timing measurements in our paper, which I would like to refer to. Yeah, so I think that would be the answer to the question.
Okay, thank you so much. I do not currently see a question on Slido, so let's transfer to our second speaker. So our second speaker is Annie, who is going to talk about a ridge-based approach for extraction and visualization of 3D atmospheric fronts.
Hello, everyone. Thank you for the introduction. Can you see my screen? Okay, perfect. Okay. So yeah, hello, everyone. Once again, my name is Anne Gossing, and I work at the SUSE Institute in Berlin. I'm going to present our recent work on a ridge-based approach for the extraction and visualization of three-dimensional atmospheric fronts. We introduce an innovative method that allows for highly detailed front representations for the investigation of scale interactions in frontal environments. Atmospheric fronts play an important role in mid-latitude weather dynamics. They are related to strong winds, cloud formation, and associated with 75% of extreme precipitation. This illustration of a cold front gives an intuition why frontal environments favor atmospheric convection and therefore the development of clouds. A cold and dry air mass is approaching warm and moist air, forcing the warmer air upwards as it moves underneath. In cooler upper regions, condensation leads to cloud formation and rainfall. Between those two air masses is a narrow transition zone, which is characterized by high gradients of air temperature and humidity. This zone is called the frontal zone. The front itself is commonly defined as the boundary of the warm air side of this frontal zone. For a better understanding of the dynamics in frontal environments and the interactions between fronts and small-scale convective processes, it is our goal to extract three-dimensional front representations while preserving a high level of detail of the underlying data. For the extraction of fronts, we use three-dimensional ERA 5 reanalysis data. This is the three-dimensional field of the equivalent potential temperature, which is a temperature variable that accounts for moist processes and pressure differences. We see a large cold and dry air mass depicted in blue colors, which comes from the North Pole and approaches warm and moist air as it moves towards the south. Since the frontal zone incorporates high temperature and humidity gradients, we compute the horizontal gradient of this three-dimensional field. This is a horizontal cross-section of the three-dimensional scalar field that results from taking the magnitude of the gradient. Purple and yellow colors visualize high temperature gradients. The cross-section shows a narrow zone of high temperature gradients that separates both air masses. From this zone, we want to extract the boundary of the warm air side according to the definition of a front. This can be done by taking again the horizontal gradient and its magnitude. The resulting scalar field is depicted in gray shades. As we see, this field has local maxima at the boundary of the frontal zone. So if we extract the local maxima of this scalar field, we find a representation for a front that follows exactly the boundary of the frontal zone. To do so, our approach is to extract ridges in the given scalar field. This method has originally developed by Klenert and colleagues to extract two-dimensional manifolds from strongly curved and folded thin layer structures. Ridges are defined as the local maxima of a given field. In 2 dimensions, a ridge curve can be thought of as a mountain ridge, consisting only of points that are local maxima with respect to its normal direction. Similarly, in 3 dimensions, a ridge surface contains only points that are local maxima with respect to surface normals. The 3D scalar field that we use is, as a simplified explanation, the magnitude of the second derivative of the temperature field, here visualized with grayscale. We extract the local maxima of this at the boundary of the frontal zone. Therefore, we start by selecting an initial point as a first seed. This step is completely interactive. Starting from this point, a patch of the ridge surface is computed using a fast marching algorithm. Then, further seed points are generated automatically. The respective patches of all seed points are merged to form a continuous surface. This way, we are able to extract front representations that follow exactly the boundary of this frontal zone. For technical details, I refer to either our paper or the paper of Klenert and colleagues. We compared our ridge extraction approach with existing contour-based 3-dimensional front visualization methods developed by Beckert and colleagues. Therefore, we looked at the frontal system associated with Cyclone Friederike and visualized our results in Math3D, a 3-dimensional visualization software for atmospheric data. The contour-based method extracts zeros of the third derivative and filters them such that only those zeros remain that coincide with the extrema of the second derivative along the warm air side boundary of the frontal zone. So we can expect our fronts to be at the same location as the contour-based fronts. However, computations up to the third derivative can introduce larger numerical errors compared to computations of the second derivative. Furthermore, contour-based methods require data smoothing to receive coherent front representations. Otherwise, we would only receive loose patches. When we compare both front visualizations directly, we see that they follow a similar path. But in some regions, they deviate, especially where the ridge-based fronts exhibit greater curvature, although we expect them, as I said, to be at the same location. So which of them represents the data more accurately? Let's have a look at the underlying data. The vertical cross-section shows the temperature field, with blue colors for cold and red colors for warm air. The gray shadings represent the temperature gradient. The dark area in the yellow box depicts the actual frontal zone as found in the data. So we can observe that our ridge-based front in green follows the boundary of the warm air side of this frontal zone. Now, when we look at the unsmooth contour-based fronts, they follow a similar path along the boundary of the frontal zone. When we compare this to the contour-based fronts that have been smooth, we see a deviation from the actual front line. Therefore, we can conclude that the ridge-based approach produces more accurate front visualizations, especially when the structures are curved. So I presented an innovative ridge-based approach to extract and visualize three-dimensional atmospheric fronts with no smoothing required, ensuring that features are represented at the same level of detail as the original data. The ability to use a lower derivative compared to contour-based methods reduces the numerical error. This approach has therefore the potential to significantly improve the investigation and understanding of atmospheric dynamics in frontal environments. Future work will include an automated procedure for the initial seeding to enable statistical analysis of front features. We also want to test this approach on higher resolution data and investigate front convective cell interactions. This ridge-based approach is integrated in the three-dimensional visualization software Amira. Thank you very much for listening.
Thank you. Let me start with the first question. When you take some initial seeds and grow those patches and then stitch them together, how is there any variability with the ending results based on your choice of the seeds?
Oh, definitely. The result varies according to the seeds. So as I said, at the moment, the seeding is interactive. And so I select the region that I want to, where I want to extract the local maxima. But as I said, we want to develop an automated seeding procedure with conditions for setting the initial seedings.
Just to follow up on that, because of this, there might be some amount of uncertainty with the final results. Have you thought about how to convey the uncertainty information?
Yes, we haven't done that yet, but we thought about it. We want to also look into the statistics and the variance of the final results.
Yes. So there is one more question on Slido. I would suggest you discuss further over a Discord. We will have to switch to the third speaker. Thank you very much. Our third speaker is Camilla. All right, so our third talk of this session is by Camilla, who's going to talk about investigating the Apple Vision Pro spatial computing platform for GPU-based volume visualization. Please go ahead.
Thank you very much. Hi, everyone. So my name is Camilla Hrycak, and I work at a CGVIS group in Duisburg. We investigated the Apple Vision Pro for GPU-based volume rendering, and in this brief presentation, I will share our findings with you. Why did we look specifically at direct volume rendering, you might ask? Because it is already a computationally intensive task on a desktop, and doing it in virtual reality presents even greater challenges. So if you consider that you have a workload. Additionally, maintaining a high frame rate is crucial to prevent issues like cyber sickness, which can occur when the performance lags behind the real-time demands. But before we're getting started, I need to establish two key assumptions. So the first assumption is that extending scientific visualization into XR is beneficial. Given the substantial number of publications on volume rendering in XR, we can reasonably assume that this assumption holds. Secondly, given Apple's track record of setting industry standards and becoming a dominant player at markets like smartphones, smartwatches, or headphones, we can assume that Apple's Vision Pro has the potential to become a significant and influential product in the VR market as well. With these assumptions in mind, let's now take a closer look at the hardware that powers the Apple Vision Pro and how it supports volume rendering in an XR environment. Okay, so the Vision Pro includes two main processors. We have the R1 processor, which is like a sensor coprocessor, and it is responsible for XR fusion and real-time video processing of the surroundings. And then we have the M2 system on a chip, which is also used by Apple notebooks and consists of an 8-core CPU with a 10-core GPU. This, in combination with 16 gigabytes of RAM and up to 1 terabyte of flash storage, makes the Vision Pro well suited to handle computationally intensive tasks, such as volume rendering. Okay, with the hardware covered, let's now shift our focus to the software side. Our studies were conducted on visionOS 1.3, with most of our findings still applicable to the current OS version 2.1. visionOS offers a variety of display modalities. Items can be displayed in windows, which serve as canvases for presenting 2D data. Alternatively, 3D objects with triangulated geometry can also be displayed within size-restricted volumes, allowing for placement within defined spaces. In addition to placing objects or data within restricted compartments, visionOS also offers extended reality through two modes: a mixed space corresponding to augmented reality and a fully immersive space corresponding to virtual reality. Here we've got two examples for a mixed space and a fully immersive space application. The downside to this is that in mixed space, the rendering is only achievable through the use of shader graphs. visionOS does not support programmable shaders or 3D textures, which limits the ability to perform direct volume rendering effectively. This leaves us with three options. Either we avoid doing direct volume rendering altogether, or we use indirect volume rendering as an alternative, for example, when we extract isosurfaces, or we have to implement axis-aligned slicing. What we did in our group is that we implemented and examined axis-aligned slicing for the mixed space and a raycaster-based volume rendering in full immersive space. For the raycaster-based volume renderer, we also tried out different settings and measured changes in the performance. So now let's take a closer look at the results. The slice-based volume rendering performs well with very small data sets, as can be seen in the top left corner. Beyond that, the performance drops significantly. For the raycaster-based volume rendering, we investigated the various settings. So we checked out the standard settings, which means that the early ray termination is on and we have illumination. And for these settings, it performed comparably well for all the data set sizes that we investigated. But then when we switched the early ray termination off, we could see a decay in the performance for the biggest data set that we checked out. And the performance was measured here in milliseconds per frame. So the key takeaway here is that while the slice-based volume rendering works out for very small data sets, the raycaster-based volume rendering provided reasonable performance for small to medium data sets. The slice-based rendering couldn't maintain sufficient frame rates for fluid animation, even for the small data sets, whereas the raycaster did, in the tested condition of 20% screen coverage. Finally, we want to extend our preliminary work, and there are several promising directions that we can explore to further improve the volume rendering on the Vision Pro. First, we want to implement a bricked out-of-core ray-guided volume renderer to be able to handle larger data sets, because the data sets that we have investigated so far were rather small. Then we want to investigate the fine control of foveated rendering, because we think that the performance might benefit from foveation also. And also we want to consider the on-chip tensor processor, which is the neural engine, and tap into it to further optimize performance. Okay, with this, I'm already at the end of my talk. So yeah, I think we still have a couple of minutes for questions.
Thank you very much. While people are typing their questions on Slido, I'm going to ask my first one. You mentioned that your experiment showed recasting works better than slicing for medium to slightly large data set. How big of a data set are you referring to, and what are you hoping for?
We'll just go back to the table. So we had the C60 atom, which is like 64 units in cubic. And the biggest one that we had was 412 cubic.
And does this already experience some amount of delay for the recasting, or this?
Yeah, so for the raycaster, the delay was experienced when the early ray termination was switched off. So here with illumination, there we could see a significant decay, but otherwise it was fine. And the slice-based volume renderer already gave up at the dataset, which was 128 cubic.
I see. Okay.
So I think, yeah.
Yeah, and I guess we have a little bit more time. Would you say a bit more of your future work in trying to expand the volume size, and what do you plan to do, and how far would you hope to push for in terms of data size?
So we hope to be able to render data sets of a size of 4K cubic. That would be our goal, that we can smoothly render them. And yeah, so we want to have this bricked out of corrugated ordering, so to be able to process the data on the device, obviously, and not to have to do tethering or anything. Then for the foveation, which is a bit interesting, so we're not 100% sure, because with a head-mounted device, the thing is that you look at the object of focus, obviously. So you kind of always render what you're looking at, right? Because it's in your point of it is in your point of focus. So, so we just tested it as a kind of a add-on right now, so on and off, but there might be a chance that there's like a sweet spot which we could find, which has really like an impact on the performance. Yeah, and so the Apple M2 chip is known to have this neural engine part, which is in particular useful for matrix operations and parallel processing of for example, AI networks. And we were hoping that we're not 100% sure how or in what direction to use this. But yeah, we wanted to dive in deeper into the stuff in here and just check out how we could benefit from having this extra properties on the chip for the volume rendering.
All right, thank you very much. So let's switch to the next speaker. So our next speaker is going to be Siyuan, who's going to talk about a comparative study of neural surface reconstruction for scientific visualization. Please go ahead.
So, hi everyone. I'm here to present my work for VIS 2024 on neural surface reconstruction. And so what exactly is neural surface reconstruction? The basic idea is to use neural networks to learn a 3D surface from 2D images. So the motivation of this work to address a key challenge: how can we manipulate and visualize surfaces when the original volume data for the surface is not available? Neural surface reconstruction allows us to reconstruct 3D surfaces from surface rendering images, enabling us to view these surfaces from various angles and adjust rendering techniques for improved visualization. It also allows surface-based analysis. So our goal here is to find the best approaches to reconstruct surfaces, particularly when applying to surfaces used in scientific visualization. So for our study, we compared 10 methods and put them into 3 groups. For the first group, it consists of neural radiance fields, including NeRF, TensorF, and Instant NGP. So the references are listed below. The second group covers neural closed surfaces, which includes IDR, News2, and NeuroAngelo. And Group 3 focused on open surface methods, includes NEAT, NUDF, and NeuroUDF. So these methods use different surface representations. The first group used occupancy grids to represent surfaces. So each cell in this grid either marked as empty or occupied based on the density threshold. Signed distance fields, known as SDF, represent surfaces using orthogonal distance to the surface and using sign to indicate inside or outside. So all the methods in Group 2 and NEAT from Group 3 are using this representation. Unsigned distance fields, on the other hand, don't differentiate between inside or outside, which is suitable for open surfaces. As the name can tell, both NUDF and NeuroUDF use this representation. So we prepare 3 datasets for each group of method. And the first group use Nix, Tangara, and Vortex. These are all isosurface of volume data. And the second group has iota, combustion, and supernova. These are more complex surfaces, evaluating closed surface methods for surface reconstruction in like more fine details. And the third group contains 5 critical points, Martian lob, and solar plume. So these are all open surface with clear edges. So we first compare the methods qualitatively by the appearance and the visual quality of extracted surfaces. As you can see from the visual results, the neural radiant field methods in Group 1 perform not good. So the reconstructed surface were noisy. In contrast, News, which is from Group 2, performed significantly better because it reconstructs smooth and accurate surfaces due to the continuous SDF representation. And we also conduct a neural rendering comparison, and we render the surface directly from the models without extracting the polygons. So in this comparison, News2 and NeuroAngelo has very good quality and with fine details, while the others are having like blurry renderings. So for the quantitative analysis, we use several metrics. So for the surface rendering, we measure PSNR and LPIPS. And for the reconstructed surface, we use transfer distance. So we measure 2 types of errors, which are missing parts and the redundant parts. So we also provide training time and the model size for each method. So for example, in this full comparison, we can see that methods have their own strengths, but most important number would be the transfer distance. So therefore, we would claim that NEDF produced the best quality open surfaces. So for 5 critical points. So note that the transfer distance here is presented in 2 components instead of the sum. So what are the key findings? The SDF and UDF methods are generally preferred over occupancy grids because they provide more accurate surface reconstruction and also more smooth surfaces. And News2 would be the best choice for closed surfaces because it uses more advanced architecture and offer a very good balance between quality and efficiency. And the surface can be reconstructed by News in several minutes. And for open surfaces, NUDF shows promising results, but still have room for improvement, especially for training speed and quality in details. So the other problem is the opaque surfaces and will cause significant occlusion if it has complex geometries, and it have heavy impacts to the reconstruction accuracy, and particularly when the number of training view is limited. So lastly, we provide a benchmark dataset for future research in this area, and we hope this contributes to further exploration. So you can find the dataset as at this link. So this is our acknowledgement, and thank you for listening. Let me know if you have any questions.
All right, thank you very much. While people are typing question in Slido, I have my first question. Would you please go back to the slide on key finding?
Mhm.
So you mentioned that there is a difference in performance between closed and open surfaces. Is open surfaces typically more complex for neural models to handle? And furthermore, what do you think are the major issues that future models should try to address?
Open surfaces are not necessarily more complex, but reconstruct surface, so extracting surface from unsigned distance fields would be more complex than extract surface from SDF. So basically because there's no difference in like inside or outside, and which causes you too hard to detect whether the surface is present. And especially when you want the open surface to have like just one layer instead of like 2 layers. So sometimes it will cause the method to reconstruct surface with border type to mimic an open surface, but not actually like the true open surface. And for the future works, I think it's just basically we're focusing on the how to reduce the training views and how to be more like generalized so they can overcome the difficulty when some part of the surface cannot be seen from any training views.
All right. Thank you very much. I don't see additional question on Slido, so let's move on. And thank you very much. Let's move on to the next speaker, Thomas. Thomas is going to talk about visualization of 2D scalar field ensemble using volume visualization of the empirical distribution function. Please go ahead.
Yeah, thank you very much for your introduction, Bay. Just checking you can see my screen, right? And you can hear me. Perfect. That's wonderful. So due to time's sake, I will just jump right in. Analyzing 2D scalar field ensembles is a common task, for example, to study climate simulations. To characterize the uncertainty in these simulations, it is usual to show the mean and standard deviation. While easy to interpret, this reduces the information to just two values at each point, but may hide other features of the value distribution. Some of these features can be easily observed while plotting 1D distributions, but it is rather difficult for multidimensional distributions, like in the case of scalar field ensembles. In our research, we investigated a further technique to show the distributions at each point. Here is an example of our visualization based on a climate change simulation for the visual analysis of relative precipitation change at the end of the century. This here is a volume rendering of what we call a cumulative height field, where in this case, the 2D plane consists of locations on Earth, while the zeroth axis is precipitation change in %. The visible volume, which resembles a colored cloud, shows the pointwise central quantiles and their spread. The colors are proportional to the precipitation change, mapping red to decrease, blue to increase, and white for no change. Hence, locations with mean a decrease in precipitation can be seen as red valleys, while blue mountains indicate that the precipitation increase was at least partially simulated. For example, we can see here that towards the North Pole, there is a slight increase in precipitation, which seems to have a low spread. Now here at the Pacific, we can see a very interesting region. It is very long, indicating a large spread, and has both blue and red colors, meaning that both an increase and decrease of precipitation were simulated. Using further views of the volume has the benefit of giving a better overview of the scene and improve visibility. For example, with a view from the top, we can spot regions that suffer an extreme precipitation decrease or increase rather easy. Let's say now we found a point of interest, for example, this one here. To show further details, we can use more views, showing cross-sections along the coordinates components of the point. We call these cross-sections the cumulative function graphs. With cumulative function graphs, we can get further information like the actual spread of each point's distributions, or see if some of them are skewed. For example, if we take a closer look here, we can see that this cumulative function graph that the distributions are indeed skewed. So how does this work exactly? First, we see the members' values for each point as samples from some unknown distribution. With the point-wise samples, we can approximate the 1D distribution functions. We use a non-parametric approximation, the empirical distribution function, or EDF for short. The EDF is a function mapping the scalar values to cumulative probability, which ranges from 0 to 1. So then we can compute an EDF at each point, and then for a given scalar value, we can get a point-wise cumulative probability. If we consider the codomain as a further axis, we can abstract this as a 3D scalar field, which can be visualized using typical methods, for example, direct volume rendering. Direct volume rendering requires an appropriate transfer function, though, which is not trivial to design. To illustrate the possible mappings to optical properties, let's first take a look at the 1D case, corresponding to visualizing a 2D scalar field, which we call the cumulative function graph. There are many color mapping options, for example, mapping the cumulative probabilities linearly to lightness, to a blackbody radiation to emphasize different quantiles, or symmetrically to lightness to emphasize the central quantiles and median. Further, we could use the original codomain values and the cumulative probabilities together using a 2D color map. For example, if there is one codomain value of interest, a divergent color scale can be used to give a further visual cue about parts of the distributions below and above the value of interest. Let's get back to the direct volume rendering for the 2D case. For the transfer function, we can use the color mapping of the 1D case, with the only missing part being the definition of the opacity mapping. For example, this could be done with the cumulative probability of 0 being fully opaque and linearly decreasing towards full transparency at the value 1. Or to focus again more on the central quantiles and median, the opacity can be set to some maximal value at the cumulative probability of 0.5 and linearly decrease to full transparency for the values 0 and 1. We can use a 2D transfer function using the 2D color map and opacity mapping, enhancing the view of the central quantiles. This way, we can get a better overview of where the distributions are located with reference to the codomain without having to resort to a data axis. With this transfer function, we can see which parts of the distribution are above or below a given value of reference. We tested our method using the climate change simulations of the Max Planck Institute Grand Ensemble, consisting of various scenarios. One example application is to compare visually the relative precipitation changes between two scenarios, for example, the most optimistic and most pessimistic ones, like done in this image using the volume rendering of the cumulative height fields. They both are rendered with the 2D transfer function, and we can see major difference between both scenarios. It can be seen that the optimistic case has almost no changes, except for some regions, as a rendered volume is shown almost as a white cloud, so it can be said that central quantiles had no major changes. On the other case, the pessimistic scenario shows major changes overall, as can be seen by the numerous red valleys and blue mountains. Now, concentrating more on only one scenario, and further investigating some point of interest, we can use multiple views as shown before. Further, as the simulation goes from 2006 to 2099, we can use animation to show the changes over time. Or we can vary the coordinates component-wise around some neighborhood to get some further insight of the surrounding area and seeing if the neighborhood has maybe some similar properties as the point of interest. Summarizing, today I showed the cumulative height fields, a further visualization for ensembles of 2D scalar fields. This method is based on the point-wise empirical distribution functions, shown using a 3-dimensional true volume visualization techniques. I presented some transfer functions that we tested, but there are certainly many more that can yield useful results. For the future, there are many points that have to be addressed, like further testing with other datasets, especially from other domains, comparison to other methods, investigating further transfer functions, and improvements of the 3D visualization. Thank you very much for your time, and now I'm open for questions.
All right, thank you very much. So while people type in question on Slido, I have my first question. So when you are developing this empirical distribution function over, say, a collection of an ensemble member, do you have a sense of the stability or uncertainty associated with your empirical distribution function? What I mean is that if I add more ensemble member or I sort of change number of ensemble member, how sensitive is this visualization change with respect to your testing data set?
Well, that's a very interesting question, actually. Well, it is theoretically known that with more samples from some distribution, you get a better approximation. So I would say it is very dependent on the underlying distributions. If you have a distribution with a very large spread, then you can have a lot of jumping until you converge to some point. And then in comparison with other distributions that have a very low spread should be rather stable and not change so much. But that is distribution dependent.
Yeah, I guess a follow-up question, let me see if there's any question on Slido. A follow-up question is how sensitive is this with respect to, say, an outlier instance on your ensemble? If you have one single ensemble member that is an outlier, how is this visualization change with respect to an outlier?
Mm-hmm. Well, I would say that it's dependent on the transfer function used. For example, you have an outlier that is really large, for example, that would shift a little bit the distribution so that you get the value 1, that's the maximal value, at a higher point. But if you have a very low opacity for such values, then it shouldn't make such a difference, if I'm not mistaken.
So maybe we'll take this conversation offline.
Yeah, of course.
Yes. All right.
Thank you for having me.
Thank you very much. So let's move on to the next speaker. Next, we will have Sangwon, who's going to talk about text-based transfer function design for semantic volume rendering. Please go ahead.
Yep.
You are in a presenter mode. You need to switch to
Yep.
the other. Yeah, thank you.
Are you good now?
Yes.
All right. Hello, everyone. My name is Sangwon Jeong, a PhD student at Vanderbilt University, and I'm presenting on our short paper, Text-Based Transfer Function Design for Semantic Volume Rendering. We'll call this T2TF in short. Thank you all for being here. Our short paper starts from the fact that the volume rendering is a tedious process. Take this for an example. At first, you may not see anything. Only when you tweak the opacity transfer function, you start to see a silhouette of what the volume might be. This process is iterative. Here, after you found the transfer function, you may want to remove the bushes, which requires further adjustment of the transfer function. Secondly, finding a realistic color function is even harder as it requires one to match different colors to different opacities. This is an example of a rendering that applies a color function which took a good 2 or 3 minutes for me to find. And it's not even remotely close to being realistic. In response, our work introduces an automatic method for optimizing both opacity and color transfer functions based on semantic descriptions of the volume. By semantic, we mean that the user provides a description in natural language. Now, T2TF can take these kind of natural language input and generate a transfer function that aligns with the description. For example, it can render a snow-covered tree based on the prompt as seen here. T2TF also handles more complex descriptions. For instance, it can render a volume with elements like brown pot, silver branches, and golden leaves. Additionally, our method is versatile enough to apply to many different types of volumes. Now, next, let's briefly cover some background. The objective of volume rendering is to visualize 3D data sets by simulating light interaction with the volume. This process involves mapping voxel values to visual properties like color and opacity, which is accomplished by the transfer function. The transfer function defines how internal structure of the volume appears based on their intensity. Next, a vision language model allows us to optimize this transfer function without needing a ground truth rendering of the volume. Vision language models compute a similarity score between an image and any given layer, label, or description. For instance, an image of forest here would score high for label nature, but low for something unrelated like urban. Next, let's move on to the methods overview. At the beginning, a user provides a natural language description of the object that they want to render, along with optional descriptions of objects they wish to avoid. Now, these text inputs are encoded by the text encoder of a vision language model, producing individual embedding vectors. Simultaneously, a volume renderer creates images of the volume using initialized transfer function and random camera poses. These images are then encoded by the image encoder of the vision language model, resulting in individual image embeddings. When we then compute a similarity score between the text and image embeddings, this objective is to optimize the transfer function to maximize the score for the positive description and minimize it for the negative descriptions here. The score guides the iterative optimization of the transfer function in each step. Next, we'll dive right into results. Here we present a gallery of rendered volumes, demonstrating T2TF's effectiveness across various types of volumes. For example, user can prompt internal structures such as skeleton or organs, as shown as the fish example shown here. In another case, users can prompt materials like the wooden gift box, where T2TF accurately finds a color function that matches the description. The method also handles more abstract prompts, such as colorful, effectively generating the appropriate transfer function. T2TF can also be applied to scientific volumes, and it allows users to identify specific parts of the volume, like the bag example here, where users can have some items highlighted. In T2TF, so we employ 3 optimization objectives. The first is contrastive objective, the semantic description of the volume. Second is the density to control overall light transmittance. And third is the regularization objective to simplify the found transfer function. In the next slides, we will see how these individual optimization objectives contribute to the final result of the rendering. In the following results, I am only using a positive description of an object that I want to see. We can observe that it finds transfer function for them quite effectively, but it could be helpful to have a negative prompt for objects that we wish not to see. Let's say that we do not want to see the skull or the face or the skin, but only the teeth. We can provide prompts that will suppress rendering of all others except for teeth. In T2TF, alongside the contrastive loss, we can optimize towards some density prior. This helps to obtain a rendering that is clear. Let's take this first example. Using a density prior results in a fuller turbulence as shown on the right side. And also in the second example, density prior helps finding a more solid metallic textures as well as removal of ambience. Lastly, we introduce a regularization term in our optimization objective, which enables us to obtain a simpler transfer function. Here, first, let's focus on the transfer functions themselves, and first notice how similar both of the renderings are with or without the regularization term. However, when we take a closer look at the color function of the example in the first row, we can see that the regularization helps to find a simpler result. Likewise, the same can be said for the opacity function. A more complex opacity function on the left side is, as seen in the last renderings, is unnecessary, and it has to go. Now, finding a simpler transfer function is helpful in case the user wishes to make fine adjustments after the transfer function is automatically found by T2TF. We conclude with the limitations of our work and potential future work. Now, always not the case, the high detail prompts or poor initialization could result in a poor local minimum. And as we are using a bit heavier model, a vision language model, this is a non-interactive method that requires optimization over multiple iterations. Now, we want to take our work and extend this to a multi-dimensional transfer function, as we are experimenting with only 1D transfer function. And to tackle the poor local minimum problem, we wish to use multi-stage coarse-to-fine prompting that will allow us to guide the volume rendering to something a bit more stable status. And lastly, we would like to employ a more powerful multimodal model than the ones we used here. That was all, and thank you for attending my talk. Now we'll move on to question and answer.
All right, so there's two questions on Slido. The first one is very interesting work. Is your code available for others to give it a try?
Excuse me, can you repeat that?
Is your code available?
Oh, it's not available. I can, if you contact me directly, I can probably will work something out.
Okay, cool.
I haven't, I haven't.
Yes. Okay, cool. The second question is, have you tested how well the prompts work for localized comments? For example, make the top leaves of the tree red and the lower leaves green.
That is very localized, I would say. I did in the as we've seen in the first few slides, I did test the case where we separate the tree branches and the tree leaves, but I haven't tried such a localized optimization. That is an interesting experiment to run, and yeah, we would like to include that in our next iteration of the development of this research. Thank you.
All right. Thank you very much. We're going to move on to the next speaker, Pratham, and he's going to talk about multi-user mobile augmented reality for cardiovascular surgical planning. Please go ahead.
Hello, everyone. My name is Pratham. I am a researcher at Georgia Tech. Today, I'll be presenting our work on multi-user mobile AR for cardiac surgical planning. Let's begin by learning about the current process. Currently, what do surgeons do prior to heart surgery? What if I told you that the current process is extremely involved, where multiple surgeons inspect a 3D printout of a patient's heart model? The doctor then performs slices across different planes to view the inner features of the heart and obtain a very strong understanding of this model. As you can imagine, this is a very tedious and irreversible operation that requires access to very advanced 3D printing technology that a lot of hospitals don't have direct access to. Is there any way we can simplify this? Yes, there is. Presenting AR Collab, the first multi-user mobile AR-assisted surgical planning tool that allows doctors to collaboratively inspect a 3D model of a patient's heart prior to heart surgery. Let's look at a quick demo of AR Collab and what it can achieve. On the left, we have an iPad, and on the right, we have an iPhone. We see that on the left, Dr. Ray signs into the device while Dr. Sam signs into the iPhone. They can see each other in the available devices section and then tap on the other device's name to connect. Once connected, they can press the Begin Session button to initiate a collaborative session between both the devices. By pressing the heart button on the bottom left of the device, Dr. Sam can import a heart model, which is then displayed on both the devices. Dr. Sam then uses finger gestures to interact with the heart, rotating the model and scaling it up to make it clearer to see. You can see that this change is also reflected on Dr. Ray's device. Then, by pressing the toggle switch on the bottom right of the screen, Dr. Ray enables the slicing mode and then manipulates the slice on the heart model, performing a cross-section across a different angle. We can see that this change is also reflected on Dr. Sam's device with an indication that Dr. Ray is controlling the heart. Dr. Sam then takes over, going back to the view mode and making the model bigger. Once satisfied with how the model looks, any doctor, in this case Dr. Ray, can go ahead and press the Save State button on the top right. This captures the current state of the heart with its slices and orientation and allows any user in the session to view it at a later time. Now, let's dive into some of AR Collab's features that make it useful for collaboration in surgical planning. First, AR Collab is designed and built entirely in iOS, allowing it to be run on iPhones and iPads. This ensures that the app is designed for portability, since doctors are generally on the move. Next, AR Collab uses intuitive, familiar gestures to facilitate collaborative model interaction. By panning across the screen, a user can rotate the model in that direction, and this change will reflect for all devices in the current session. Similarly, Pinch gestures allow for scaling the model up and down as well. We also introduce an additional twist gesture, allowing the user to rotate the model along the z-axis, which is perpendicular to the device. AR Collab also features a reversible omnidirectional slicing feature, which allows users to perform cross-sections across any direction in the model. Unlike the physical models, these slices can be reversed at any given point of time. This is also collaborative, where changes from one device will be reflected on all the other devices within the session. Finally, we conducted a usability evaluation to understand how useful our tool would be in a real-world scenario. We recruited 3 cardiothoracic surgeons and 2 cardiologists from the Children's Healthcare of Atlanta, and we had them evaluate the features of the app while performing their surgical planning workflow. We used the Think Aloud process during the evaluation and concluded the study with a Likert questionnaire. From the study, we gathered the following insights. First, AR Collab's collaborative features were easy to use and intuitive, which facilitated efficient surgical planning. Then, anchoring the model in physical space allowed surgeons to move around the heart model and improve their interaction. They noted this feature as intuitive and useful for examining the heart from different angles. The most important aspect of collaboration for the surgeons is portability, as it allows them to interact with the heart model anytime and anywhere. Additionally, real-time interaction ensured that all doctors received all updates simultaneously, also improving their ability to collaborate. From the questionnaire, we received positive feedback, with the participants agreeing that this app improves collaboration and supports surgical planning. They found the multi-user aspect of the app very useful and extremely easy to use. Here are some quotes from the participants that highlight their experience with AR Collab. You can see that they found the gestures very easy to use and understand, and they foresee this being used in planning in the future. All in all, they did agree that AR Collab improves collaboration. And that's all I had for you. If you're more interested, you can check out the code and the paper at bit.ly/arcollab-git, or you can scan the QR code to get to the same URL. Thank you.
Thank you very much. So while people think about questions, I will start with my first one. You mentioned multi-user support. What is the limit of the number of users in the system?
Currently, as it stands, we can support up to 4 users, but we plan on conducting more studies and more evaluations to see if there is a need to extend that.
Okay. Let's see. Yes, so there's a question. What's the plan for future evaluation? Do you plan to directly compare the AR app with the physicalization?
Yeah, that's a great question. So for future evaluations, we plan on continuing to work on the app a lot more. Based on our current evaluations and our prior work, we've received feedback from the doctors that we plan to continue iterating upon. They already enjoy using this a lot more than physical models, given the restrictions that are imposed with physical models. We plan to add additional features such as a distance collaboration feature, allowing the doctors to utilize the same multi-user augmented reality approach, but not requiring them to be in the same space at the same time. We also plan to work with their feedback more and possibly integrate like an additional Vision Pro or headset application that they can work with alongside the mobile AR application.
All right. Okay, let's see. All right, there's no additional question. Thank you very much. Let's move on to our last speaker of the session. We have Ho Jun, who's going to talk about active appearance and spatial variation can improve visibility in area labels for augmented reality. Please go ahead. You are in a presenter view.
Can everybody?
You need to switch to, yeah, it's now current presenter view.
Can everyone see my screen and hear me?
Now we can. Please go ahead.
Okay. Great. Hi everyone. Today I'm going to talk about how we can use AR labels to they can cope with dynamic real-world environments. And I also have a live audience here at Boston VIS. So AR area labels are AR overlays on an environment. These labels can highlight visible features, such as on the left, showing the Brooklyn Bridge by Anne and colleagues. And these labels can also visualize invisible features, such as on the right, where Liao and colleagues show the location of a brain tumor on a patient's head. But real-world environments are dynamic and diverse, as we see in this video of Dubai's marina. On the left, we see in a time-lapse the lighting change throughout the day. And on the right, we see that the environment complexity changes from busy skyscrapers to clear sky. So AR designers should ensure label visibility across these dynamic environments, but the environments where users view AR is often unknown. So this means that we need to use active AR labels, which can change appearance based on environment conditions. Existing solutions for active text labels use outlines or move the label to a less cluttered area, but these solutions are less applicable for AR area labels. For example, we may want to highlight features that are within the label, like Hrycak and colleagues did here. So what goals do we have for our AR system? First, we want AR area label shapes to be clearly visible, regardless of their environment. And we also don't want these labels to occlude environment detail. So to address these two goals, we build an active AR system for the video see-through AR setting. Our first task is to use contrasting colors to draw attention to the label. If the label color is too similar to the environment, then the label will not be seen, like this blue label on a cityscape during dawn. So we need to find the label color that is perceptually distant from environment colors. Suppose we have some input RGB color from the environment. We can map this to the CIE LED space, which is perceptually uniform, and use the delta E 2000 distance to find its most perceptually distant color. But computing this distance in real time is expensive, so we pre-compute this for all RGB colors to make a 3D lookup texture where each coordinate stores most perceptually distant color. Next, we're going to analyze the environment region under the label. Naively computing average environment color often results in these muddy colors because, as in these two very different images, most regions contain many different colors. So instead, we first sort environment pixels into these 27 equally sized bins in the RGB space. And we derive the characteristic environment color by taking the average color of pixels from the most popular bin. And this binning makes sure that we don't end up with indistinct background color. And then we assign to the label the most perceptually distant color from this characteristic environment color. In our resulting system, we can assign label colors automatically based on environment colors. But what if you want to highlight the environments that is underneath the label to reduce environment occlusion? We can use spatial variations by looking at the distribution of environment pixels under the label. So here's our current situation. We have a characteristic environment color and its most perceptually distant color as the label color. We take distances between this characteristic environment color and all environment pixel values underneath the label and add these distances back to the distant color to derive the final label pixel values. And as we see in this video on the right of on the left of a train station during nighttime, we see that spatial variation can reduce environment occlusion without significantly changing label color. And we can observe a similar effect in this video on the right of the same station during dawn. To evaluate our system, we invited 18 participants with normal vision to our study. We used fixed green labels as our baselines. Given the human visual system's high green sensitivity, existing research in AR labels found that green labels are the best in enhancing label visibility and also reducing perceived environment color changes. So including these two baselines, we had six label visualization modes with different levels of opacity and spatial variation. All our user studies took place in a Lewakis Pro headset. In our 3 test scenes, we presented AR labels and label visualization modes in a random order within a 2 alternative forced choice setting. Upon choosing their preferred label, label visualization mode, we asked the participants to select the rationale behind their choice. And we used the Spring Rank algorithm to generate rankings based on pairwise comparison results. In general, our active color generation mode with 40% opacity and spatial variation was most preferred. But if we take a look at results across all 3 scenes, we see that none of the 6 modes perform consistently better than others. And across all scenes, participants predominantly chose background under the label was more visible as their rationale. Now let's take a look at results from individual scenes. In an environment where the colors were similar to the baseline colors, all our modes outperformed the baseline. This may be because our active color generation modes were better than the baseline at creating high contrast with the environment. And in a nighttime scene with high lighting contrast, our label visualization mode with active color generation and spatial variation was most preferred. But a baseline mode outperformed ours in a bright outdoor scene. And in this bright scene, the color changing effects with spatial variation may have appeared very drastic, causing some participants to say that the resulting label colors looked a little unrealistic. So our visualization modes outperform the baselines in some scenes. And this shows that we need to consider the characteristics of the human visual system when designing AR systems. But our mixed results show that we need a better perceptual proxy function. To conclude, active AR label visualizations with model based on the human visual systems will enable us to use AR in more diverse contexts. Also, I'm looking for internships for next summer, so please feel free to reach out to me via email. Thank you.
All right, thank you very much for the talk. We have 2 questions coming up. The first one, does the perceptually most distant color take color blindness into account? Are there models that can take color blindness into account?
Currently, our model doesn't take color blindness into account. And all of our study participants had normal vision. But I know that there are some models that can computationally model color blindness, which may be something that is interesting to include in our future study.
Okay, so the second question is how many labels can be in a scene and how computationally expensive is a computation per label?
So in our particular experiment, we only had 1 label per scene, and we could compute the colors and spatial variation for these in real time.
All right. I don't see additional questions. Please feel free to go to Discord to have further discussions. And let's thank all our speakers for this session. And enjoy the rest of the VIS conference. Thank you.